please display their posters before 1 o'clock in the quadrangle by the in the pandal near the next to the auditorium. Please, once again, please, the people who have poster presentation today, please go and fix their posters there. I request the chairman of the session, Dr. Henrik Tapso, and Dr. Professor G.D. Yadav, his eminent scientist award lecture he is going to deliver. And next, Button Davis and Bipin Vora will follow. I request Button Davis and Bipin Vora also to come on to the dais and sit in the...
A video first.
Yes, good morning. It's a pleasure to co-chair this session. And the first speaker is not foreign to any of you. You have seen him just a few minutes ago. It's Professor Yadav. Professor Yadav is Dean of University Institute of Chemical Technology at Mumbai University, and he is the head of the Department of Chemical Engineering. He holds 25 patents and has written more than 200 technical and scientific papers. He has received numerous national, Indian and international awards, and he has just received another important award. He's also a member of many of the important Catalysis journals advisory board, and has also received the Innovator of the Year award in 2006. So it gives us great pleasure to welcome Professor Yadav to the podium and address us this morning and talk about developments of novel solid superacid catalysts and their applications in industrial reactions. So please.
Thank you, Mr. Chairman. I will take precisely 30 minutes because I have to rush to Delhi, so I will not take anything more than that. It's my great pleasure to present before you some of the works which we have done, and I would like to pay tribute to Professor S.K. Bhattacharya, the founding member of the Catalysis Society of India, for his pioneering contributions, and to the Catalysis Society of India for honoring me today. If you look at sources of organic pollutants, these are multi-stage synthesis, insertion of substitutions like halogen, amino, nitro, sulfonic acid groups, and all of these affect the color and odor of the final compound. And this will involve use of hazardous inflammable solvents and mixtures of solvents, or if you use hazardous synthetic precursors. So the pollution potential increases in a complex molecule, in particularly multi-product industry and those who work on small scale in comparison with refineries. So if you look at some problem here. So in the so-called dozen principles of green chemistry, the most important principle of that is catalysis, and all other principles are derivatives of these catalytic principles, and that's what I personally believe. So they are all derivatives of the central theme of catalysis. Now, as far as my research group goes, we have been working in multi-phase reactions in green chemistry, in which catalysis also is a central theme. So here, on one hand, we have been working with more than 2 phases, 3-phase reactions. In certain cases, the phases may be, nano or micro. They may be catalytic or non-catalytic, as the case may be. On the other hand, we have catalytic processes, including synergism with energy. It could be ultrasound or microwaves or UV. Now, in the some problem also with this. Your own computer, my dear.
It's his own computer.
Okay, so this our group is currently 15 PhD students, 5 master students, and 3 postdoctoral. And we work, some of the work which I am presenting is based on the 45 doctorates and 42 master students which graduated from my laboratory. Now, one of the interesting ideas which we have been already working on, and this has been used, is having so-called cascade engineered processes where you can use the same catalyst again and again, and it may be more than one reaction using the same reactor. Now this requires a lot of reaction engineering principles apart from catalytic principles. So this will reduce the separators as well as the number of reactors, and this fits into the principle of green chemistry. The other is the kind of work which we have been doing. Mostly this has been related to solid acids, microporous and mesoporous acids, the sulfated zirconia, clays, heteropoly acids, some zeolites, ion exchange resins, and the so-called UTCAT series of catalysts, which the materials which were developed in our laboratory and named after University Department of Chemical Technology, as the name suggests, including some mixed oxides. We have also worked on noble metals and biometallics, and recently we have started work in encapsulated noble metal catalysts. Multiple input is created for this. Okay. So here, in this particular case, we have developed this eclectically engineered catalyst. This is UTCAT1, UTCAT2, heteropoly acids, CCM, dodecatungstophosphoric acid, and this series of new catalytic materials, some of which have been patented already. Then in non-solid bases, we have modified hydrotalsides. We have developed some new synthetic methods, including they use as nanocatalysts. Somehow it is not working. It said GDR, though I had to say that. It's a folder. I'm sorry about this mismatch of the computer with the projection system here. Folder is there. I have. Yeah. I say?
You can present from here. So you can watch. So from there you can't see.
Okay. So, okay, next. So this we had this series of catalysts where UDCAT 1, UDCAT 2, these are again based on zirconia. Heteropolyacids and modified heteropolyacids next. And this UDCAT 3 through UDCAT 7 type of catalyst. Again, one of the three is the redox type of catalyst. 4, 5, 6, 7 are solid superacids next. And then we also worked on modifications of hydrocalcides, including novel synthetic methods, and their use as nanocatalysts next. In the area of biocatalysts, we have work going on supported enzymes, on novel supports, use of microwaves and enzymes, and chiral separations. Next. We also work on phase transfer catalysis, and a number of these reactions, including engineering aspects of this. This is liquid-liquid, solid-liquid, solid-liquid-liquid, omega phase, and 4 phases, and a different type of microwave irradiating reactions. Next. Then ionic liquids, where they are used as phase transfer catalysts or catalysts or solvents, are using them in combination with microwaves. Next. Then we have the project going on supercritical carbon dioxide, where synthesis of novel materials and nanocomposites being done, including this as a reaction medium from catalytic reactions. Next. Then in multi-phase reactions, we also deal with mass transfer with chemical reactions, and these are not necessarily catalytic reactions, but they could be non-catalytic reactions, like gas-liquid solid reactions, 2 liquid phases gas-solid reactions, and here also role of nanophases, which are not catalysts, but they increase the rates of reactions in selectivity. Next. Then in cascade engineered catalysis, we work with solid acids where more than 2 to 3 reactions are combined in a single reactor, phase transfer catalyst, solid bases, and again these 4-phase reactions. Next. And in energy engineering, we have also worked on enhanced oil recovery, where novel methods of oil production from depleted reservoirs and working reservoirs. We have done network modeling of multi-phase flow through porous media. We have developed novel visualization techniques, including micromodels and microreactors. We have dealt with percolation processes, particularly bond percolation, side percolation, and mixed percolation. And recently, we have also been working on hydrogen production and storage. Next. And as far as the group is concerned, we have now established a Center for Clean Technology, which is a UGC center under the Potential of Excellence program. And we also have been sanctioned the Center for Nanoscience and Nanotechnology, which is a part of 150-year celebrations of University of Mumbai's birth, along with Madras University and Calcutta University. Next. Now, as far as solid acids concerned, our journey began with sulfated zirconia in 1989, when I was doing an industrial assignment in rubber chemicals division of Kosil, and that is where we started this work. Next. Next. And as far as acid catalysis is concerned, we know that right from cracking to hydration, dehydration, a large number of reactions require acids, and this is where solid acids can make a large difference, particularly where there are sequential reactions or parallel reactions, where selectivity of the desired product is most important parameter, and then scaling up this for reactor design. So there we may have Bronsted acid, Lewis acids. Next. Then as far as these homogeneous catalysts are concerned, we know that is a neutralization of acidic mixture is a big problem that leads to the effluent treatment problem. It leads to the corrosion. Next. Then loss of yield. And next. and presence of impurities in the final product. And this is where novel solid acid catalysts, which do not leave the acidic centers, will be most important. Next. So if you look at this, unfortunately the slides are not totally seen, but this is the acidic scale. You can look at the Hammett acidity function. Superacids are above, Hammett acidity function of -12. So this is -16 is sulfated zirconia, which is the solid superacid. You see magic acid is something like -20. So we have been working in this region, on this side, whatever is shown here, all these catalysts we have been working on. Next. For example, when we started firstly, and this was based on an industrial project where we wanted to react aniline with hydroquinone. And this is a sequential reaction, and so there could be oligomerization to, polymerization. So this reaction has to be controlled, and this is where we started our work on sulfated zirconia, which was published. And later on, we absorb, isobutylene in paracrisol, and this goes into antioxidant industry. And this particular product, where acylation reactions are conducted, this goes as a veterinary drug. Next. Then we had production of yara from naphthol. This unfortunately this is not seen here. Then again a reaction of cyclohexene with paracrisol to give very important chemical, and this on hydrogenation is a very important perfume. So you have both O selectivity and C selectivity. And again, you can have the reaction of diphenyl oxide with one of the alpha olefins, C10 or C12. Next. And reactions of diphenyl oxide, right from benzyl alcohol to dibenzyl ether to benzyl chloride. This also gives a very important chemical. This can be converted into a perfumery chemical, or it can be high temperature heating medium. At the same time, you may have esterification reactions like thalligonide, right? And when some of the work we published, in this paper, sulfated zirconia in my mesoporous microporous materials. Now this is quoted this year as the citation classic with 30 citations. Next. As far as this is concerned, then we thought, why not change the acidity of these solid acids? If you look at this, sulfated zirconia when treated with sulfuric acid at 650 degree calcination temperature gives us -16 Hammett acidity. Next. So what it means, if we change the nature of the sulfating agent, if we change the method of addition, you change the pre-calcination and post-calcination and the calcination temperature, you can introduce different sulfur content in the zirconia. At the same time, you can change the crystallinity of the phases, and all this can also be coupled with the nature of the strength of acidic sites. Next. So you can see that it is possible to introduce sulfur content. Unfortunately, this is not clear for here. You can see here you have 5.6, about 84% of sulfur, and you can have 4.8% of sulfur, or typically it is 4% of sulfur. And both tetraphenyl and monoclinic phases are there in the sulfated zirconia. So one can change the sulfur content and change the nature of phases. Next. So then what we did, first we did with boric acid, phosphoric acid, and sulfuric acid, and you can see that the surface area here is 92, here it is little less, and at the same time these are not super acids as a comparison, in comparison with sulfated zirconia. Next. So at the same time, pure zirconia has both acidic and basic centers, but sulfated zirconia is much better catalyst. And this is how we started the work. Next. And then we went on developing these various catalysts. And as I mentioned earlier, this is a mesoporous material, this is a shape-sealing material, this is a redox material, this is again mesoporous material, and these are the highest superacidity reported so far in literature. And again, UDCAT 6 is a mesoporous material. Next. So for example, in UDCAT 1, which we have a US patent, then suppose that this can be used for cracking, nitrations, acylation, alkylations, and some of these reactions are given here. For example, the alkylation of ethyl benzene with ethanol, in which I know a lot of industries, petrochemical industries, find it of interest. This can, using dilute ethanol, one can alkylate this, and we have shown this using UDCAT1. Next. Well, then also, you know, you could react cresols with MTBE, for example. This is a very interesting material. You can get alkylated cresols. This is again, this goes in oxidation industry. Next. UDCAT2 is a self-selective catalyst, and in fact, you can see sulfuric zirconia is over here, and UDCAT2 over here. We can actually close this gap very nicely, and this depends on the pre-treatment process. I won't go into the details of this. Next. And so here, by using this catalyst, you can have cyclization reactions like citral, isopropyl, and you can have nitration reactions. Next. In the case of nitration reaction particularly, using this particular catalyst UDCAT2, you can see that almost 45% conversion. The para to ortho ratio is the highest, 13.2 to 1. Next. In the case of this redox catalyst, we can have both oxidation of benzyl alcohol to benzaldehyde, hydroxylation of phenol to hydroquinone in catechol, and also the alkylation in this oxidation of this particular compound, that is sulfur to sulfoxide. This goes as a very important drug intermediate. Next. In the case of UDCAT4, again alkylation of mesitylene, you can see that this PET surface area, in comparison with, unfortunately that next part is not seen, but UDCAT4 gives us the best catalytic activity. Next. So again, this is done with alkylation of mesitylene with isopropanol. There are many series and parallel reactions, so this becomes a very interesting reaction engineering problem apart from this selectivity of this particular product. And you get propylene, you get diisopropyl ether as the another co-reactant, and this will depend on temperature and W/Fa0 ratios. Next. So in this particular case, we had studied independently all these reactions and proposed a very interesting model which has been published in Langmuir. Next. Next. So in UDCAT4, many other reactions were done, like alkylation of toluene with benzyl chloride is a typical reaction to study the acidic strains. Then again, this mesitylene, and also you can see that diphenyl alkylation with tertiary butanol. Next. In UDCAT5 again, this is published in Journal of Catalysis. We studied benzylation reactions and also esterification reactions. Next. This you can see that this is a very important perfumery product, so we had studied this reaction as well. Next. In UDCAT6, we had worked on TAME, tertiary amyl methyl ether, and you can see that UDCAT6 with a 95% conversion, the yield of these two olefins is very high, and the total yield of TAME is something like 18%. This is just a single pass conversion. Next. So in the case of combination of clays and heteropolyacids, next. Next. So you can see that the supported heteropolyacids and the clays, there is a combination, and clays have typically a surface area K10 is something like 230 meters square a gram, and when you support clay, the heteropolyacid, the surface area goes down substantially, but at the same time it gives much more conversion and yields. Now what happens exactly in this particular case is that heteropolyacids sit on certain junctions in the clay, and therefore there is a sort of selectivity which is because of blocking of certain channels which are not available for the reaction. So many secondary reactions are avoided by that, and this we had used in for instance in the case of alkylation of benzene with dodecene, and we could get totally different selectivity. Next. So again, this reaction synthesis of MTBE from tertiary butanol and methanol, this we produced the first report in KinCon in 1995, and you can see that this particular catalyst 20% on this at K10 gives a very high selectivity to MTBA, something like 99% with 71% conversion. Next. Again, we studied alkylation of aniline with tertiary butanol. Okay, this gives us C alkylation and not N alkylation. Again, the same catalyst is very effective. You can see that this is the one. Next. Then alkylation of phenol with MTBA, similar thing. This supported dodecatons to phosphoric acid on clay is a very good catalyst. Next. The oligomerization of DODC is a very important reaction in lubrication industry, and here also this particular catalyst is very good. And later on, what is done is this is hydrogenated to get the lubricant. Next. Acylation of mesitylene with acetyl chloride. Once again, this particular catalyst gives a very good, this is a supported catalyst. This gives a very good risk. You can see that it gives 100% monoacylated product. Next. So this particular reaction has been carried out using number of processes. For example, this is phenyl alcohol with methanol to get phenyl methyl ether, which is a perfumery which goes in the fragrance Kevra. This is a very interesting reaction. Again, you can see that this bisphenol making from phenol and acetone. Again, this particular catalyst is a very good catalyst. Next. Similarly, alkylation, I have already mentioned rhodecyl benzene. Then again, MTBA reaction. Next. And variety of other reactions which are, for example, this is a very good reaction of where you can change the selectivity between C alkylated product and O alkylated product in reaction of phenol with cyclohexene. And on further hydrogenation, this gives a very important perfume. Next. Once again, you can see that alkylation of aniline, for example, with MTBA gives this para-tertiary butyl aniline, or also it can give ortho-tertiary butyl aniline, but it does not give any N-alkylated product over here. Next. Again, you can see acetic anhydride reaction. Okay, this is a Veratol reaction. This is again a very important reaction in the perfumery industry. And in this particular case, people have used zeolite beta, and zeolite beta gets deactivated. However, we find that this particular catalyst does not get deactivated for at least 5-6 runs. So this is a better catalyst, particularly in acylation reactions. When we have ethers of this kind, they are deactivating the catalyst. Next. We also worked on ion exchange resins as catalysts, and ion exchange resins are very good, and particularly they were found to be very good for MTBE synthesis. Unfortunately, MTBE is no more produced or banned in many parts of the world, but at the same time, that was its maximum use, industrial use. Now you can see that alkylation of styrene and with orthoxylene. This is a very important reaction in industry. What we found that this reaction also deactivates the ion exchange resin, and if you modify the surface of this resin by suitable treatment, the deactivation is stopped. And this was also coming out of the industrial consultation which I was doing. Next. Again, you can see that this gives a 100% atom selectivity because this ester is again a perfume. So if you have this alkylation with cyclohexene, we get very interesting reactions. Next. So like this, we had done a number of reactions of industrial importance, and these were right from esterification to alkylations to to nitrations to oligomerizations. And what we found that the catalyst can be tailor-made depending on what you are interested in. Particularly what happens in liquid phase reactions, unlike the vapor phase reactions, the deactivation of the catalyst and the loss from run to run can be very significant, and that is where the engineering has to be very good. So particle size, and if you increase the particle size, for example, then you will have the intraparticle diffusion limitation. So therefore, the catalyst synthesis and reuse is very, very tricky. Next. So this, these are some of the mathematical, formulations and design equations which have been studied for variety of reactions. For example, we found in acylation reactions, these are typically Ely-Riedian type of mechanisms. Next. This particular catalyst were partially substituted heteropoly acid with cesium. You can see the acidity of this catalyst is brought down. At the same time, this becomes a nanomaterial. And when it is loaded on clay, this requires a lot of, we had done a lot of experiments to develop a synthetic method. We found that the surface area of this material, is almost 210 meters square a gram and against 230 of clay, K10. So from heteropoly acid, about 108 to 210 is a substantial increase in surface area when we reduce the particle size, and this becomes a nanomaterial. And this again gives very interesting selectivities. Next. So you can see that about this is 204 here, this is about 107. And next. So you can see that when you benzylation of anisole is done with this type of catalyst, this particular catalyst is 20% zinc chloride supported on K10. This is not a reusable catalyst, although for single run it may give very high, convergence. But this particular catalyst is reusable, and this, of course, this is less acidic than zinc chloride on K10. But at the same time, this nanomaterial is a very good catalyst. Next. Well, that catalyst could be used in, a xylene mixture or acylation by using benzyl chloride. Now, depending on the mole ratio, temperature conditions, and catalyst loading, I can produce any of these three materials, which are again very important ketones in industry. They can be further subjected to hydrogenation to produce a variety of chemicals. So this gives us a way to us to make different chemicals from xylene mixtures. And we have studied these reactions independently, taking pure xylenes and mixtures of xylenes to make this type of claims. Next. Again, in diisopropylation of phenol, this can be done by using isopropyl, propylene, or diisopropyl ether. And this final product over here is a drug, okay, and this has a great demand. So now this particular compound can also be synthesized by using this nanocatalyst, cesium substituted deuterium cation to phosphoric acid on K10. Next. So to conclude, we have developed a series of new solid superacids catalysts, and these are characterized and used in a number of reactions of industrial relevance. What I avoided is the mathematical formulations for want of time, and also going into the details of the reaction. Since this is a sort of overview of the work which we have been doing, I may not have given many details, but any of you who has any queries, I'll be very happy to answer them because these are all published reports, so there is no problem. Next. So I've been supported through large number of organizations over the years. So I have some 43 projects. When I counted last, I found I had done some 43 projects with variety of these agencies, some of them multiple times. Next. And of course, this is some of my past and current collaborators are seen here. I think one of them is here in this audience. And next. And this is my current group. And I must thank all of them for participating in the joy of doing something new, and I thank once again the Catalysis Society of India for honoring me with this Professor S.K. Bhattacharya, eminent scientist. Thank you very much.